In this video, we will use Kirchoff's laws to find the currents flowing through this circuit. Before we begin applying Kirchoff's laws, we first look at our circuit and see if there are any resistors in series or in parallel with each other. Looking at this circuit, I could see that these two 1 ohm resistors are in series with each other, and these two 1 ohm resistors are in series with each other. If you are wondering, does the fact that there is a battery between these two resistors matter? The answer to that will be no. You could convince yourself that these two resistors can be considered to be in series because whatever current flows through this resistor must also flow through that resistor. And one characteristic of resistors in series is they will all have the same currents flowing through them. So therefore, I could combine these two 1 ohm resistors into a single equivalent 2 ohm resistor. So I will go ahead and combine these two resistors. I will just erase this 1 ohm resistor and change this into a 2 ohm resistor. And similarly, I could combine these two 1 ohm resistors into a single 2 ohm resistor. So I will just erase this resistor and change this into an equivalent 2 ohm resistor. The first step in applying Kirchoff's laws is to draw and label the currents flowing through our circuit. If the direction of a current is not obvious, we should just guess on the direction. I will choose to draw the current flowing through the left side of the circuit is flowing in a clockwise direction. I will guess that the current flowing through the right side of the circuit is also flowing in a clockwise direction. And I will guess that the current flowing through the center of the circuit is flowing upwards. I have to label these currents, so I will label the current flowing through the left side of the circuit as I1, the current flowing through the center of the circuit as I2, and the current flowing through the right side of the circuit as I3. The currents I1, I2, and I3 are the unknowns in this problem that we will be solving for. Before proceeding, there is a comment I would like to make about the directions of currents I1 and I3 that we chose to draw here. I do not actually believe this current will be flowing upward through the battery and this current will be flowing downward through the battery. The reason I say that is if you think about a battery has a positive and a negative terminal. The positive terminal is designated with the longer line in a battery symbol, and the negative terminal is designated with the shorter line in a battery symbol. What a battery does is a battery produces an EMF, and that tends to push charges from the negative terminal to the positive terminal of the battery. So in a nutshell, the battery is trying to push current in this direction. Looking at the three batteries in this circuit, I see all three batteries are oriented so that their negative terminal is below the positive terminal. We know that the three currents cannot all be flowing upward through this circuit because that would imply we have more current entering a junction up here than exiting a junction. Therefore, current must be flowing quote unquote backwards through the battery from the positive to the negative terminal. Looking at the voltages of these batteries, and if I think of voltage loosely as how hard a battery is trying to push charges in a certain direction, I see I have two 4-volt batteries and a 2-volt battery. Because this battery has a smaller voltage, I think it is most likely that current will be flowing downwards through this battery as opposed to the other two. However, as I said previously, it is okay to guess the direction that a current is flowing when you are applying Kirchoff's laws. And if we guess wrong, that will just be shown when we solve for the unknown current and find a negative number. Therefore, it is okay if I guess wrong on the direction that the current is flowing through a circuit. So for an instructive example, I decided to choose the directions of the currents as shown here. So now we will look for all the junctions in this circuit and apply Kirchoff's junction rule. So if I look at this circuit, there are two junctions. One junction is right up here near the top of the circuit, and one junction is down here near the bottom of the circuit. The junction rule states that the total current flowing into a junction must be equal to the total current exiting a junction. Looking at this top junction, I see current I1 and I2 are flowing into it, and current I3 is flowing out of it. So applying the junction rule to the junction over here, I could write I1 plus I2 is equal to I3. If I apply Kirchoff's junction rule to the junction down here, I see current I3 is flowing into the junction, currents I1 and I2 are flowing out of the junction. So if I were to apply Kirchoff's junction rule down here, I would get I3 for the current flowing in is equal to I1 plus I2. Looking at these two equations, I see they actually are identical. This second equation does not give me any new information, so I am free to just ignore it. At this point, we have one equation with three unknown terms in it. We could apply Kirchoff's loop law to find two more equations containing these unknowns, and then we could solve for all the unknown currents in our circuit. I will choose to have a loop that begins on the lower left side of the circuit, and we will travel around the left side of the circuit in a clockwise direction. So the path that we travel around the circuit will look like this. As we cross the circuit element when we are traveling around this loop, we will record the change in voltage using the rules from the previous video. And when we return to our starting point, we will set the total change in voltage around this loop to be 0. I begin by walking upwards through my circuit. The first circuit element I encounter is the 2-volt battery. Because we are traveling from the negative to the positive terminal of the battery, in other words, from the short line to the long line in the battery symbol, the change in voltage as we cross this battery will be plus 2 volts. We then turn to the right and encounter no circuit elements as we are moving to the right. We then turn downwards and encounter a 4-volt battery. Now we are traveling from the long line to the short line, from the positive to the negative terminal. That implies the change in voltage as we cross this 4-volt battery on this path will be minus 4 volts. Next, we encounter a 2-ohm resistor. I see that the direction of the current flowing through this resistor is upward, and the direction that we are traveling is downward. Because we are traveling in the opposite direction that the current is flowing, the change in voltage as we pass this 2-ohm resistor will be plus IR. So I could write plus I2 times R is 2 ohms. We then turn to the left and we encounter this 2-ohm resistor. Now we are traveling in the same direction that the current is flowing through this resistor. So the change in voltage as we cross this 2-ohm resistor will be minus IR. The current flowing through this resistor is current I1. So I will write minus I1 times 2. And when we return to our starting point, we set the total change in voltage around this loop to be 0. We now have two equations with three unknown terms in them. We will apply Kirchoff's loop law again to a different loop in this circuit. I will choose to travel around the right side of the circuit in a clockwise direction. Let us choose to begin our path at the lower right side of the circuit. I'm going to draw this loop in a different color just to help it stand out from the currents and the other loop that I drew previously. If we are traveling in a clockwise direction, I will initially be moving to the left. Then we travel upwards through the center of the circuit. We turn and travel to the right when we get to the top of the circuit, and then we turn downwards and return to our starting point. We will again travel around this loop and record the change in voltage as we cross the circuit elements in our loop, and when we return to our starting point, we will set the total change in voltage to 0. When we are traveling to the left, we encounter no circuit elements. We then turn upward, and the first circuit element we encounter is the 2-ohm resistor. Unlike the previous loop, we are traveling upwards through the center of the circuit. We are now traveling in the same direction that the current is flowing through this resistor, so the change in voltage as we cross this resistor will be minus IR. The current flowing through the resistor is I2. The resistance of the resistor is 2 ohms. So the change in voltage as we cross this resistor in this path is going to be minus I2 times 2. The next circuit element we encounter along this path is the 4-volt battery. We are now traveling from the negative terminal to the positive terminal of the battery, from the short line to the long line. So the change in voltage as we cross this battery will be plus 4 volts. As we continue along this path, we turn to the right and encounter this 2 ohm resistor. We are traveling in the same direction that the current is flowing through this 2 ohm resistor, so the change in voltage will be minus I3 times 2. So I write minus I3 times 2. We then travel downwards and we encounter this 4 volt battery. Now we are traveling from the positive terminal to the negative terminal of this 4 volt battery. So the change in voltage as we cross this battery will be minus 4 volts. And we return to our starting point and set the total change in voltage around this loop to be 0. At this point, we have 3 equations with 3 unknown terms, so we could solve for the currents flowing through this circuit. Aside from using the signs of the currents that we find to give us information about the directions that the currents flow through the circuit, the rest of this problem is just algebra. Looking at these 3 equations, let us first use the third equation. The third equation could be rewritten as minus 2I2 minus 2I3, and here I have a plus 4 and a minus 4 which cancel. So I could write minus 2I2 minus 2I3 is equal to 0. This implies that I could write I2 is equal to negative I3. Let us take this relationship and plug it into the first equation. I could think of this relationship also as I3 is equal to negative I2. So using that relationship, I could then rewrite the first equation as I1 plus I2 is equal to negative I2, and that gives me I1 is equal to negative 2I2. I will now take this result and plug it into the second equation. I have plus 2 minus 4, which gives me minus 2, and then I have plus 2I2, and then I have minus 2I1. So I could write that as minus 2, and here we said I1 is negative 2I2. So I have negative 2I2. And then we set all of that equal to 0. This equation can then be written as minus 2 plus 6I2 is equal to 0. And this tells me I2 is equal to 1/3 amp. Now that we have a result for current I2, I could use this equation and this equation to find currents I1 and I3. Therefore, I could say I3 is equal to negative 1/3 amp from I2 equals negative I3. And from this relationship, I could say that I1 is equal to negative 2/3 amp. Now let's think about what these results mean. Current I2 is positive 1/3 amp. The fact that this current is a positive number indicates that we guessed correctly on the direction that this current flows. The current is flowing upwards through the middle of the circuit. Currents I1 and I3 are both negative numbers. That indicates that our guess for the direction that these currents flow was wrong. Current I1 is actually going to be flowing downward through the 2 volt battery, and current I3 will actually be flowing upward through the 4 volt battery. Notice that these results match the expectations we discussed earlier in this video based on the voltages of the batteries in this problem. Our final result is that the 2 volt battery has a current of 2/3 amps flowing downward through it, and both 4 volt batteries have currents of 1/3 amps flowing upward through them.